All right, today we're going to be talking about Chapter 9, Lesson 1. This is all about functions. So a function is dealing with a relation with independent, which would be x values, and dependent, which are y values, variables. Each input results in exactly one output. So our input, independent, and x values, they're all representing the same thing. And we have dependent, y values, and our output all being the same thing. And each one of those we call the domain and range. Now, in this first set here, notice how the domain, each one of these four values, results in exactly one value over here. This represents a function. Each input results in exactly one output. This data set over here, we have 3 inputs and 4 outputs, and this too results in this output and this output. So because this input results in more than one output, this is not a function. All right, so let's look at some examples here. Example 1, it says determine whether each relation is a function. We have 2 of them here, A and B. So let's look at A here. We have 5 different ordered pairs. Each ordered pair has a different x value. Remember, x values are the first number in an ordered pair. It also represents the input, the independent variable, or the domain. There is a different input for each of these ordered pairs, resulting in a different output. So exactly one input results in exactly one output each time. So this is a function. The reason why is because each input results in exactly one output. Now letter B. We have a table here. Again, these x values, this is my input. The y values are the output. So we have 2 inputs that are the same, and they result in different outputs, which means that this is not a function. Because the input of 3 results in 2 different outputs. And the input of 3 should result in just one output if it is a function. Now we have another method that we could use to help us do this, but it's really only going to be beneficial when we're given some kind of graph. The other method that we're going to use is called the vertical line test. And what we do is we take a pen or a pencil or something that's straight, and all we do is we move the pen from the left side to the right side. if for some reason two dots intersect with this line at the same time. So far we're good, 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 all the way through. So the vertical line test, if two ordered pairs touch the line at the same time, the data is not a function. The reason for that is because these x values here, these are my inputs. These here are my outputs. So as we're going through this, if it intersects with a line twice, or a dot twice, that means one input would result in two different outputs, and that's not okay. So let's go ahead and start looking at an example dealing with this. So explain whether the graph shows a function, and explain. I'm going to use a ruler because a ruler is very thin and straight. So starting from the left here. Here, only one dot intersects. Moving along, same thing, only one is touching. Same thing, still only one. Same thing, still only one. Ooh, here we have two dots touching, which means that this is not a function because it doesn't pass the vertical line test. So let's go ahead now and talk about how we can describe relationships. So we can describe a relationship by either doing it as an equation or a function. Now, when we write it as an equation, I'm going to write the same thing both times. We're going to have y equals, say, 3x plus 5. In this case, x represents the input, y represents the output. In function notation, we actually write it like this, where x still represents the input, but now f of x represents the output. The way this is said is a function of x is 3x plus 5. We evaluate it exactly the same way we would normally evaluate an equation. In fact, our inputs and outputs would be the same regardless if it's written as an equation or as a function. The reason why we like functions is because sometimes we use 2 or 3 functions in a row where we would say use this equation and then use that output for the input of the next one and use that output for the input of the next one. But with a function, we can actually put all of those together into one big step, which makes it just a little bit quicker to use. So let's talk about just some simple functions here. If f of x equals 6x plus 5, find the value of each function. So the way that we do this is f of 7 equals 6 times 7. We substitute the 7 where the x was, and we add 5. So 6 times 7 is 42. 42 plus 5, so f of 7 is 47. For letter B here, exactly the same thing. We're going to say f of negative 4 is equal to 6 times negative 4 plus 5. Again, wherever we see an x, we're going to substitute in negative 4 because negative 4 is the input. 6 times negative 4 is negative 24. Negative 24 plus 5, so f of negative 4 equals negative 19. All right, so let's go through one last example here. So it says Ms. Newman spent $8.82 buying postcards that sold at 49 cents each. Identify the independent and dependent variables, and then write a function to represent the total cost. So we're going to split this in half. Over here, we're going to talk about the variables. Over here, we'll write our function. So our independent variable, this is going to be the input, what everything is depending on. Total cost, cost per postcard. So really, it would matter how many postcards you bought, would be your total cost. So this would be postcards purchased. And then our dependent variable would be the cost, because the cost depends on how many postcards you purchased. Now, our function. We can use whatever variables we want, but we still have to start with f. So, this right here is my independent variable, which happens to be the number of postcards that I purchased. So I'm going to use a variable of p here. So I'm going to have a variable, the same thing right there. Now this depends on how many postcards are purchased. This right here, this whole thing will represent the cost. So this cost would depend on how many postcards there were and the cost of each postcard. So our function would be 0.49 times p. Letter B, it says use the function to determine how many postcards that Ms. Newman actually purchased. So if I have f of p equals 0.49 times p, and I know the total cost was $8.82, I can work backwards to find what the input was. So $8.82 is equal to 49 cents times each postcard. Now this is a pretty simple and standard one-step equation. We would want to divide both sides by 0.49. And if we do that, we would get 18. And of course, because this is a word problem, we would have to say Ms. Newman purchased 18 postcards. All right, that is going to be the end of lesson 1. If you have any questions, please let me know.